Well, there's more to the story than that, but that's a quick summary. I'm actually a Kansas farm boy. Grew up on a farm just outside Council Grove, Kansas. That's where I went to high school, was Council Grove, and came to KU in '75. Got my BS in astronomy, as Hume says, and I also was in Air Force ROTC while I was here at KU, and so I went into the Air Force for 23 years, and that's during that period of time, Air Force put me through for my master's degree at USC in engineering management. I worked space systems with the Air Force for that entire career. Did a lot of work with NASA also while I was in the Air Force. One of the things I did in the Air Force was tracking of satellites, Earth satellites, man-made satellites around the Earth, and all the leftover junk up there as well. One of the things that I did early in my career was set up the what we called the collision avoidance program for the space shuttle, when the space shuttle first started going up, to assure that after spending all those billions of dollars on the space shuttle, we didn't take one down by running into a piece of debris somewhere up there. So I spent a lot of time in the Air Force career in orbital dynamics, orbit determination, determining where objects were going in orbit around the Earth. And so the job I do today is just a macrocosm of that. Instead of man-made debris around the Earth, I'm tracking all of the debris that's left over from the formation of the solar system, all the asteroids and comets, to try to determine if any of them are going to run into the Earth, and figuring out what we're going to do about it if we do find one. So you've probably seen movies like Deep Impact and Armageddon. Well, I'm the real Bruce Willis. Try not to look so disappointed. So I'm going to talk to you about what has euphemistically been called the hard rain. That actually comes from a book that John Lewis wrote several years ago about the threat of asteroids impacting the Earth, the so-called hard rain. Now we see this every day, at least every night. If you go outside, you'll see shooting stars. Well, that's just the small end of the spectrum of the material that is still left in the solar system, the dust from comets and asteroids that's out there, shooting stars, meteors. But that phenomena is caused by very small stuff. The average size of what is called meteors is a grain of sand. Some of the larger ones, though, can be as bright as or as large as a grain of rice. But what's causing all that energy, release of energy, is the speed at which they're traveling at. Kilometers, tens of kilometers a second, tens of thousands of miles an hour. And when it hits the atmosphere, that kinetic energy has to dissipate somewhere, and it's in the ionization of the atmosphere, brightness of light of that interaction, the so-called hard rain. The infall to Earth from dust and debris left over from the formation of the solar system. This is a natural process. This is how the planets were accreted. And there's still, planets are still accreting that matter. Some 100 tons of matter still infalls to the Earth every day. So the Earth is still growing. little nomenclature here. In space, if an object is smaller than a meter in size, meter is a little over 3 feet in size, it's called a meteoroid. If it's larger than a meter, and the International Astronomical Union just figured this out just in the last year, has determined the designation between what is an asteroid and what is a meteoroid. If it's larger than a meter, then it's called an asteroid. Meteor is just when that matter hits the atmosphere and causes this bright phenomena. That word goes all the way back to the ancient Greeks, phenomena in the sky. And we've finally figured out what was causing that, and that's, as I said, an infall of dust into the atmosphere. Once it hits the ground and is recovered on the ground, then it's called a meteorite. Recent news, you may have heard of some of these significant meteorite falls. There was one just recently in Michigan where we detected the entry of the object into the Earth's atmosphere. Figured out using both spacecraft resources and weather radar, by the way. The weather radar has high enough resolution now that we can actually see meteorites falling to the ground from these events, and then we can determine where to go pick up the meteorites on the ground. And so that's kind of just a free sample return. Instead of having to send spacecraft out to gather samples of these objects, if we can find them fast enough on the ground before they get contaminated by the Earth's environment, that's a very scientific bonus to us to get that material. And from those trajectories, we can determine what the origin of the parent body was in the solar system. Usually they come from the asteroid belt out between Mars and Jupiter. And then, as I said, locate meteorites on the ground. This happened as you can see, in a snowy time in Michigan, and people going out to hunt for meteorites, or hunting through the woods and all that kind of stuff. Well, it's winter in Michigan. The place to go look for it is on the ice, on the lakes. And so we told them, go look on the lakes. And they were able to start finding samples within an hour or two after we directed them to that. So this is just one event of many that have happened. Objects a meter or larger in size. These are all the events that have been recorded by our euphemistically called U.S. government sensors that have been detected around the world in the last 30 years or so. Every one of these is an object estimated to be at least a meter or so in size. Some 700 events recorded there. One great significance, though, you see the big red dot there. That's Chelyabinsk, the Chelyabinsk event that occurred back in February of 2013. This has got to be one of the best recorded events in history, with all the Russians with their dash cams. The amount of data that we have on this event is just something. Now, if you were to see that falling out of the sky in front of you, would you still be going down the road toward it? I would at least have stopped side of the road. But there's a lot of interesting footage that was taken from dash cams and security cams of this event lighting up the sky. Now, this guy at least looks at it and tries to figure out what the heck's going on. And of course, people saw the bright light in the sky. Everybody rushed to the windows to see what was going on. This happened about 18 miles above the surface. And so about 2 minutes later, when the shock wave hits, people are standing at the windows, and the shock wave blew the windows in on them. So there was quite a few people that were injured by the shock waves. And as you can see, it was pretty significant to blow in garage doors and things like that. And in fact, the energy release of this event, it was an object that was almost 20 meters in size, is our estimate, was equivalent to an explosion of about a half a megaton nuclear weapon. And that's the closest thing that we have, that we can think of as an analogy to the energy release of these objects of significant size as they hit the Earth's atmosphere, or large enough to hit the Earth. So some 1,600 citizens were injured enough that they had to seek hospital help, and over $30 million of damage was done. Now, this was a very small one. In fact, this is so small of object that we don't even try to track them to this size right now. But the objects that we're trying to find and prevent an impact of the Earth are a lot larger than this. But if we find something of even this size, it would be certainly something we would want to warn about, so that we tell the people, stay away from windows when you see that bright flash of light. Another event of not too long ago, a little over 100 years ago, the Tunguska event in Siberia. An object estimated to be about 40 or maybe 60. Some of the recent studying we've been doing on this event indicates it might have been a little larger than some of the initial estimates. Remote area of Siberia, thankfully. Now, why does Russia get hit so much? Russia has the largest land mass of any country, so that's why they see it so much. But they seem to be taking their share of things. But it was some 20 years before scientists actually got to this remote region of Tunguska and found that there was over 800 square miles of forest that was blown down, toppled to the ground. The area of devastation from this impact compared to the land area of a couple of major metropolitan areas, indicates that we would not want this to happen over a major metropolitan area because of the destruction that would occur of just an object of 40 meters in size. Another event of not all that long ago in geological age. Who knows where this crater is? Is this crater on the moon? Is it on Mars? Here, we got it over here. Where's Arizona, actually, but you were close. Eastern Arizona. This is the Barringer Crater, or more popularly known as Meteor Crater, in eastern Arizona. Just off of, it's between Winslow, Arizona and Flagstaff, just off of Interstate 40. And if you're ever on Interstate 40 between Winslow and Flagstaff, I highly recommend you go see this. It's quite a sight. It's a crater that's over a mile in diameter, but caused by an object thought to only be about 50 meters in size. Now, this was an iron meteor, so it was more capable of penetrating the Earth's atmosphere and hitting the surface, but also not slowed down much by the atmosphere, and therefore most of the energy was then released on the surface, blowing out a mile-wide crater. And the area of devastation of this event, if it happened in modern day, would cause effects all the way out to Winslow, Arizona, which is some 25, 30 miles away from this site. So not something you'd want happen in your backyard. Asteroid hazard has been of significant interest to both the scientific community and our government for a number of years. The event that really caused it to rise to the level of national concern was the impact of Shoemaker-Levy 9 on Jupiter back in 1994. That really showed people that this still happens in the modern age. There are still objects out there impacting the planets, And it's probably something we need to spend a little bit of effort to determine if there's any hazard to the Earth, and might the Earth be impacted. So after the Chelyabinsk event, that again renewed the concern and hearings on the Hill and those kinds of things. The administration in 2013 was supportive of our efforts, and this is maybe one of the few issues that still has pretty bipartisan support on, this is something we ought to be doing something about. But it goes, it's part of space policy that NASA has the task to find these objects and determine if any can be an impact threat to the Earth. And we administration signed off by Congress on what we ought to be doing about it through activities that have occurred in the time I've been at NASA. So all this has led up to in 2016, January 2016, we finally established the Planetary Defense Coordination Office at NASA. And the word coordination in the title is very important, because NASA is not going to do it all itself. We have to coordinate efforts across not only the U.S. government agencies and the private space sector, but internationally as well. So we are an office to lead efforts not only within NASA, but of the U.S. government, and work with our international counterparts to determine if there is an object discovered on an impact trajectory, what could it do to us, how bad would it be, is it something we need to try to do something about it in space to deflect it so it won't impact the Earth, or is it an object that's small enough and we can determine that it's going to impact somewhere in the oceans, somewhere, the Earth is 7/10 ocean, so it's most likely going to impact in the ocean somewhere, and if it's not too big an object, that really won't be too much of a problem. But if we do need to do something about it, what are the strategies, what are we going to do to prevent that from happening and protect human life? Most important part of the business, though, is we've got to find them first. If we don't know they're out there, know where they're going, know when they might be an impact hazard to the Earth, we can't do anything about them. So better part of our effort is spent finding them, determining their orbits, and finding any that could pose a hazard to the Earth. A little bit of terminology here for you. Near-Earth objects, that's an astronomical definition, is anything that comes, it's actually not related to the Earth, measured from the Earth, it's anything that comes within 1.3 astronomical units of the Sun. Well, what does that mean? Astronomical unit, of course, is the average distance of the Earth in its orbit around the Sun. So anything that comes 1 1/3 times that to the Sun are objects that are coming into orbits into the inner solar system, and therefore could represent a hazard of colliding with the Earth. There are two major types of bodies. There are the asteroids and the comets. Now, the more we learn about asteroids and comets, they were once thought to be two very distinct types of bodies in the solar system. But we're really now finding that it's just a spectrum from rocky material to, on the asteroid side, to bodies that have more ice and dust and volatile matter in them, the so-called comets. And their origin may be a little different. Asteroids tend to be in the inner solar system, and their rocky bodies are largely because they were closer to the Sun, and so any volatiles they had has already been boiled off of them, versus the comets, which are usually coming from the outer solar system beyond the orbit of Jupiter, and so they have not spent as much time close to the Sun and have a lot of volatile material with them still. And so we're trying to find those populations. that come into the inner solar system, and particularly looking for a subset of them, what we call the potentially hazardous objects. And those that are ones that truly come close to the Earth's orbit, within about 5 million miles of the Earth's orbit. And those are the ones that we want to keep track of. Most asteroids and comets will never be an impact hazard to the Earth, but there is a subset that come close to the Earth's orbit that we need to keep better track of. So the NEO Observations Program, it's actually, NASA has had this program since 1998 is when it was first undertaken. The U.S. program is the most active and prolific in finding the bodies. Our original task by Congress was to find at least 90% of the population of 1 kilometer and larger asteroids. Kind of bite this elephant a piece at a time. We wanted to, of course, find the larger ones first because they would do the most damage to the Earth, and make sure we don't have anything like that out there that's going to impact us anytime soon. And then later on, as more was looked at the problem, and we determined that even smaller objects, even on the 100-meter scale, and as I showed you earlier, even a 50-meter size object could do significant damage. Our threshold was lowered by the Congress to 140-meter sized objects and larger. And so that's a program we're currently on. Congress even amended NASA's charter, the Space Act, to say that this is one of 7 tasks that NASA is set up to do. NASA's charter doesn't say we need to go back to the moon. NASA's charter doesn't say we need to go on to Mars. But the charter specifically states that NASA will detect, track, and characterize the near-Earth object population to determine if there's any potential hazard to the Earth. They wanted us to do that when they set this up back in 2005, wanted us to complete this survey by 2020. And as I'm about to show you, we're a long ways behind the timeline on this. Currently, our survey systems are ground-based telescopes, largely, that have been adapted from other purposes. They are meter-class telescopes that were cast off by fundamental research projects in the past, but some of our university partners have adapted them more for survey purposes and made asteroid hunters out of them. So the University of Arizona runs one of our projects, the Catalina Sky Survey. University of Hawaii runs another one called the Panchromatic Surveillance Telescope and Rapid Response System, PAN-STARS. They've had one telescope operating for about 5 years now, and are just now bringing on the second telescope to be able to cover more sky. Another cast-off that we're using, this was WISE mission, the Wide Area Infrared Survey Explorer, was an astrophysics mission to map the infrared background of the sky in preparation for James Webb. But if all the imaging that it was taken of the sky, we quickly figured out, we can find a lot of asteroids in all those images. And so we adapted just using ground processing to an asteroid hunter. And after the astrophysicists were done with the spacecraft, after only a year, we took it over. This was in 2010, was at the end of its prime mission, and we've been running it ever since and hunting for asteroids. But also because it operates in the infrared, where it's a lot easier to determine the size of these objects, because what it's detecting is the heat that comes off these asteroids as they're heated by the sun. And so that signature is more proportionally representative of the size than the solar light, sunlight that's reflected from them, because if an asteroid is very light in color, it reflects more light, but if it's dark in color, it doesn't reflect so much light. And so you really can't tell the size of the asteroid by just how bright it is in the visible part of the spectrum. But in the infrared you can, because it's more representative of the size. So NEOWISE has been also a very good characterization asset for us in determining the size of these objects, not only near-Earth asteroids, but in the main belt as well. Another recent project, ATLAS, is been set up by the University of Hawaii. Now, most of these telescopes are finding asteroids that are further out, the larger asteroids as they're further out. Smaller asteroids, as they come closer to the Earth, we can detect them, but unless we're covering a lot of the sky, we won't see them because they'll get by us faster than we're able to cover the sky with the large telescopes. This ATLAS system is more agile. It can cover the entire sky in a night or two to detect anything smaller that might be on an impact trajectory with Earth. And so we can at least give a few days warning so that an area, if it were to be impacted, could be evacuated. And then finally, we work with the Air Force and the Department of Defense on their new space surveillance telescope was originally developed for tracking all the objects in Earth orbit. But as it's taking all those images of stuff in Earth's orbit, we can see the asteroids in the background, so we work with the Air Force to collect that data and process it for detecting and tracking the asteroids as well. That system was operating down in New Mexico for a couple of years as it was being developed. It's now being moved to Australia for its primary mission, but along with that, we're working with them to, the Australians as operate it are going to continue the asteroid detection mission as well. And so with that, we have a very good Southern Hemisphere asset as well, which is something we're kind of lacking right now in our ground-based capabilities. A couple of other very important parts of our network are the Minor Planet Center. Minor Planet Center has been in existence for decades, and is known within this astronomical community. If you take observations on asteroids or comets, you send your data into the Minor Planet Center, and it compiles all that data from observatories around the world for determination of the orbit of these objects. Originally it was really to who gets the discovery credit for these objects. The first guys to get their observations into the Minor Planet Center got discovery credit, which comes along with benefits of being able to name the object after your wife or cousin or whomever. There's rules about that, though. It's not that easy. So it's had a long existence, but it's a very important node for us because data from around the world comes into the Minor Planet Center, so we get the benefit of all the observations from around the world. And so NASA's Planetary Defense Program has taken over the funding and support of this center, particularly for detection and tracking of NEOs, but the rest of the astronomical community gets the benefit of it because it tracks all the small bodies in the solar system. And then our Center for NEO Studies out at the Jet Propulsion Laboratory. This is where the high precision orbit determination is done with what observations are taken, both optical and radar observations that are taken of these objects. This is the same group of folks at JPL that do the navigation for interplanetary probes that go out to Mars, Jupiter, Saturn. They put Cassini through the rings of Saturn, so they've got pretty good orbit determination software. And so we've have high confidence in their information. And they do the determination whether there's any impact potential for an object, for not only Earth, by the way, but the other planets as well. If an asteroid was going to impact Mars, we'd want to know about that because it would be a really neat science experiment to watch an impact on Mars and see what happens. We also have been working internationally for a number of years under the auspices of the United Nations Committee on Peaceful Uses of Outer Space. This is seen by the international community as one of the areas where we really do need to cooperate in space. And so they undertook with an NEO working group in the committee to determine what internationally should we be doing about this threat to the Earth. So I and a few other folks from around the world, counterparts around the world, developed a protocol underneath the United Nations as to what we're going to do. Of course, the United Nations is not a world government. What the United Nations does is by consensus of the member states, so this is all determined by the government delegates. But it was agreed that we'd set up an international asteroid warning network for all the observatories that are detecting and tracking these objects. We would share our data through the Minor Planet Center and other activities like that to determine if any object was a threat to the Earth. And if that did occur, we would provide warning to any country in the world, particularly those that don't have their own capabilities, of this threat, to develop an international response to it. And another part of that is institution of the Space Mission Planning and Advisory Group, and this is a forum for the space-capable nations to develop their technologies and techniques and work collaborative projects for developing a deflection or mitigation capability. Both these organizations have now been up and running for about four years, and is the center of our collaborative efforts on the international community. Back in last year, these are all the observatories around the world that provided observations on asteroids and comets to the Planet Center. Now, most of these observations, of course, are on objects that are in no hazard to the Earth at all, main belt asteroids. Most of them, only about a hundredth of the observations are actually on near-Earth objects, but the science community gets the benefit of all this other data that we're bringing in. Some 47 countries have contributed to the effort last year. This is our right here through the years. Back in '98, not much was being discovered, but then NASA set up its program, and that's where you start to see the rise and the discoveries of near-Earth asteroids over the years. And as we've brought on new capabilities like the Catalina Sky Survey came on back in about 2005. Pan-STARRS started some operations back in 2010, but really came on strong in 2013, 2014. And so that's what's increased our discovery rate. We're up to about 2,000 discoveries each year, adding to the catalog. We're a little bit behind this year. The weather's been pretty bad in Hawaii, and that's cut down a lot on our discoveries so far. So whether we're again break the record for discoveries per year in 2018 is yet to be seen. Our cumulative catalog to date is a little over 18,000 near-Earth asteroids of all sizes. The ones that we're particularly hunting for, the 140-meter and larger, are in the orange there. About a third of the total number. The 1 kilometer and larger asteroids, we once thought that there were over 2,000, but our current studies now show that actually it's under 1,000. In fact, precisely, according to the statistical modeling, the population of 1 kilometer and larger near-Earth asteroids is 934, plus or minus about 15. So 888 of them are now in our catalog, and so we've done pretty good on that. We're only finding maybe 6 or 8 a year now. So you see the red part of the curve is leveled off quite a bit. So we've got a pretty good handle on that size asteroid and larger. And of course, you also see there where the NASA effort started to make the difference. So how do we know where we're at? Well, the red line here, is this laser pointer? Yes, it is. The red line here, this is our predicted population of objects in each of these size bins down here. This is 1 kilometer sized object here, and larger and smaller down here. So this red curve is our model of the population. The green bars here are the number of objects that we've discovered to date in each of these bins. So you see out here on in this end of the population curve, we've done pretty well. We've almost got all of the objects into our catalog. But it starts to drop off here just below 1 kilometer or so in size. And that's because our capability to find these objects they're a lot dimmer, and so we don't have the capability to find them when they're far away from the Earth. They have to come close enough to the Earth to be bright enough for our current assets to be able to see them. So we're not doing as well down here on this end of the curve. The blue curve is the percent complete we are in that population. Now down here you're getting into small number statistics, but there's an interesting dip here at about 4 kilometers. We don't have as many here in this part of the catalog as we should, so I don't know whether there's really a gap there or what might be going on. But again, this is small number statistics. I think there's the population model shows there's about 20 objects there to be found, and we found about 10 of them. So, so that's part of what's going on there. Kind of another way to look at it, here you have the same red curve, the number found, and the blue curve. Here is where we're looking today. These are the objects from about 1 kilometer in size down to 140 meters. Our current task to find these objects in this part of the population. Against these events I talked to you about earlier. The Chelyabinsk is way down here. I'm not too worried about those. Tunguska is a little more worrisome. You know, a metropolitan area could be wiped out by impact of that size. This is the base of our survey goals right now. The big dinosaur killer is up here, a 10-kilometer size object 65 million years ago. It's believed to cause the demise of the dinosaurs. So we think we've pretty much got these. We've got some work to do in here and a lot of work to do here, because this is a little misleading. I mean, it looks pretty small, but this is a exponential scale over here, so the numbers are actually a lot more than it looks like. If we break it down and look at it this way, the population 140 meters and larger is thought to be about 25,000. And so if this pie represents that population of 25,000 objects, the 1 kilometer and larger objects are only about 4%, and we've found the greater part of those. So this is actually back in 2010. I'm sorry, let me advance this one. Back in 2010 compared to where we are today. So we've pretty much found the 1 kilometer and larger slice here. 300 meters to 1 kilometer in size, we're about 2/3 of the way complete. But these together is only about 25% of the population. It's really down in here where most of the work remains to find these 100 meter, few hundred meter in size scale, and so about 2/3 of the population is still yet to be found. Not only that, but we need to know more about these objects, and we use a number of assets to better characterize them, their sizes, composition. If we have to mitigate one, deflect it, we need to know what it's made of. How massive it is really what we're trying to get at. And so we use radar. There are 2 radars in the world that are capable of enough energy, putting out enough energy in return to be able to detect and track these things. The Goldstone radar, part of NASA's Deep Space Network, and the Arecibo Observatory down in Puerto Rico, 300 meter dish. Both of these assets are getting pretty old, hard to keep up, but critical capability that we need, particularly if we find an object that is on an impact trajectory. We also run an infrared telescope facility in Hawaii to help us in the characterization, determining what the composition of these objects are. And then we make use of some other assets that were developed for other purposes. We're still using the Spitzer infrared telescope. It's getting pretty long in the tooth, and probably not long for life anymore, but it can detect a few of these objects, and we take that data where we can. We find interesting things in our survey. This is an object found back in 2015, discovered by Pan-STARRS on October 10th. We quickly determined, and with the orbit determination, it was going to have a close pass by the Earth in October 31st. So, of course, we had to call it the Great Pumpkin. Coming to us on Halloween. Got a little press because we found this object only 3 weeks before it might hit, according to the headlines. We knew, though, pretty quickly that it was going to be a clear miss, so we weren't too worried about it. You know, the initial radar, these are radar images here that you see coming in. The initial radar image that came in when we first saw it, that first frame right there, well, that kind of took us by surprise. Halloween, you know, if you use your imagination, it kind of looks like a skull, you know. But as we got more detailed, see if I can get this one to run. Whoops, sorry about that. Ah, man. So I'm going to have to directly click on it. So we got the more detailed radar imagery in. Kind of took on a different appearance. I mean, that kind of looks like the guy in Despicable Me to me. We're always anxious to see these radar images come in and see how these things look, and can make all kinds of stories out of them. Another object discovered in 2014 by the NEOWISE spacecraft. Finally, orbit brought it close enough to the Earth that the radar could detect it here this last, well, a little over a year ago. So the radar imagery of that shows it to have this binodal shape, maybe two objects that have come together over time and are coalescing, or the other theory is it's object that is being slowly pulled apart because of its rotation rate. This looks a lot like the comet that the Rosetta spacecraft visited, the European Space Agency Rosetta, but this is a much smaller object than the comet nucleus. This is kind of the mini-me of the Rosetta comet. And again, the spectrum, as we can get more and more data to build up the characteristics of these objects as much as we can. Another close approach that we waited for many years, Florence was found way back in the 80s, but finally came close enough to the Earth for us to get radar on it this last year. And we found not only is it a fairly large NEO, almost 3 kilometers, or 3 miles, I'm sorry, in diameter. It also has two moons orbiting it. Most of the asteroids that have been found to be binary, or in this case trinary systems, have all been found by radar. You can't, they're too dim to detect that optically unless the configuration just happens to be that an occultation occurs as the moon passes in front of it, but that's pretty rare for an asteroid. And we see some really odd duck-looking objects as well. Another NEOWISE discovery that imaged, and our radar imagery is getting so good that we can actually detect boulders and such on the surface of these objects. Another very interesting discovery that hit the headlines last fall, discovered by the Pan-STARRS survey. As we determined the orbit of this object, we quickly figured out that it was not of this solar system. It's on a trajectory going so fast through our solar system, it had to have come from outside of the solar system. And we didn't see it because of the direction it came from. Came above the plane of the solar system, around the sun, opposite side from the Earth, and we didn't detect it until it had actually had to come out of the daytime sky into the nighttime sky before we were able to detect it. So it was on its way back out of the solar system before we were able to take any significant observations on it. Seems to be a very elongated object. Looks a lot like what we see in outer solar system objects, like the Kuiper Belt objects and sets. There is some interesting speculation about what this object might have been. If you've ever read Arthur C. Clarke's Rendezvous with Rama, in fact, some of the astronomers wanted to call it Rama, and we said, no, let's not do that. There's no indication that it's an alien spaceship. But we have some interesting conclusions as we track it back out of the solar system about what the trajectory is doing. There's a couple of papers that will come out here shortly with an interesting story there. Another spacecraft program that we've got going right now is called the Cyrus Rex. I'll talk a little bit about more later. But it had a close pass by the Earth in its trajectory here this last September, and it took this picture of the Earth-Moon system. This is actually an actual picture of the Earth and the Moon. Gives you a perspective on how small these objects are out. There's a lot of space for a lot of objects to come through. This is a list of all of the asteroids that came between the Earth and the Moon in 2017. One thing you see about, there's 52 in this list. And so about once a week we have an object of several meters in size that comes between the Earth and the Moon. If you know how asteroids are designated, the first digit, first part of it is what year they're found. And so you see all these were found in 2017. We didn't see them until they came close to the Earth. So these are all new discoveries in 2017, and we didn't see them until they were going to come between the Earth and the Moon. Most of them are pretty small. We're not too worried about objects like this, 4 meters, 6 meters, 4 meters, 2.5 meters. Thankfully, they're small because these are the ones right here that came closer than the geosynchronous belt of satellites. These 4 right here. The only one in this list that we knew about before, just a day or two before the close pass, and in most cases actually not until the day after, because they came from the direction. It's not until the night we can detect them. So we see them going away and go, didn't get hit by that one. But 2012 TC4, of course, found back in 2012, we had predicted of this close pass, and so we used this object to kind of test our capabilities for detecting these objects, to recover it as it came back in, how far out we were going to detect it, and how rapidly could we then characterize the object and know what it was and how big it was as it came toward the Earth, to kind of test our capabilities. So we had an exercise of the International Asteroid Warning Network using this object, TC4. A couple of these objects, though, are pretty significant size, almost 50, 60 meters, possibly. If they're dark objects, wouldn't want to get hit by one of these two. And this one, 70, 80 meters maybe in size, almost came closer than the geosynchronous belt. A tenth of the distance to the Moon is our rough rule of thumb of the geosynchronous altitude. And then the first one found in 2018, I've added it to the list here, came between the Earth and the Moon, 150 meters in size. Need to know about these before they get this close. So what would we do if we found an asteroid headed toward Earth that was going to impact us? So what we call mitigation. We're working across the U.S. government on the planetary defense capabilities in the emergency response community. The emergency response community talks about doing things left of boom and right of boom, with the boom in this case being the impact. So what do we need to do? Left of boom, detect, track, characterize these objects, and then what does the emergency response community have to do for response recovery? So we work in an international, in an interagency working group. NASA's responsibilities are out here mostly left of boom, and then we have to hand off to other folks for the emergency response. FEMA, we work with FEMA and the Department of Defense in those areas. Here's a tortured acronym for you. Interagency Working Group, DAMIAN, detecting and mitigating the impact of earthbound near-Earth objects. That was formed in 2016 to develop the national NEO preparedness strategy. And who says we can't get things done quickly? Within a year, we had published our strategy, and are now working on the detailed action plan of what all the agencies need to be doing in this area. From across the U.S. government, departments are involved in this effort, not only NASA and the Department of Defense, also the Department of Energy, and others are involved in the effort. Another important piece of what we need to know in being preparedness is how much damage could a particular asteroid do. And so part of our effort is in modeling what the effects of an impact could be through our threat assessment project. What are the thermal effects? What are the blast effects, and how far out from the entry and impact area could there be disaster response capabilities needed to model that and to be able to inform the emergency response community on what they could expect to happen. And we conduct exercises with FEMA and other elements of emergency response. We had one a year and a half ago. Impact in Southern California. This particular part of the sequence was a few months out, 5 months out. Impact, we were able to determine it was going to impact somewhere along this corridor. Our estimates on the size of the object and when it might impact. Actually, determining when the impact is going to occur is a very easy, precise part of it because we know what the Earth's orbit is very precisely, and if we can get that asteroid orbit nailed down, we know within a few minutes to even seconds as to when the impact will occur. And so the emergency response community is kind of blown away by this because we can tell them when it's going to happen, if it's going to happen. And there's no other disaster that they have that kind of information ahead of time. For this particular exercise, an object that size, we're at the impact in the Southern California area, Los Angeles area, and we targeted this one right on the Rose Bowl. This would be the area of devastation around the Rose Bowl, and if you're familiar with the Los Angeles area, this is a very wide area. This is across here is about 50 miles, so impact of a 100-meter object. If it were to happen on Florence, the area of devastation would reach to the Topeka and Kansas City on either side. So what do we do about it? Well, there's been a number of studies of mitigation techniques and capabilities. I'm going to cite the recent National Research Council, National Academies. It was done in 2012. The kind of capabilities that we have in hand that could be utilized. Most mature technology we have is a kinetic impactor. Kinetic impactor, that technology has undergone some development, of course, with the Missile Defense Agency, but I was involved in a project when I first came on at NASA called Deep Impact, where we used a kinetic impactor to run into a comet for scientific research. We hit the comet's surface and dug out some of the material ejecta from the comet so we could examine what that material was. So that's technology that we know how to build and do. Now the comet was quite a bit bigger than the average asteroid that we might have to deal with was. It was some 7 kilometers in diameter. And we might need to have to hit a asteroid that's only 100 meters across. So that's a bit more of a challenge, but we're working on that. Another mature concept is what we call a gravity tractor, and this is just using nature's own tug rope, gravity. Objects in space will have a mutual attraction to each other, and so if you keep a spacecraft beside an asteroid, as long as it's not too big, and you've got plenty of time over the course of years, that spacecraft will slowly tug that asteroid off of its impact trajectory. So another good reason to find these things well enough ahead of time, because that's a very controlled manipulation of the asteroid's orbit. We can tug it only long enough to take it out of harm's way, so to speak, and we can conduct the operation and then examine, have we pulled it far enough away, and if not, then we can continue the operation. So it's a very controlled modification of the asteroid's orbit, as opposed to a kinetic impactor where you hit it once and what you get is what you get. All these techniques work just by changing the velocity of the asteroid, its speed and its orbit, just a few fractions of a percent, an inch per second. If you do that many years in advance, will cause that asteroid, if you slow the speed of the asteroid down, will cause the asteroid to be late to the collision, and so it'll be a miss instead of a hit. So all these techniques are based upon just changing the velocity of the asteroid. You can change the velocity of the Earth or the asteroid. I choose the asteroid. This just shows how the gravity tractor would work, the station keeping off to the side of the asteroid. A enhanced gravity tractor, we might go up to the asteroid, actually collect a large boulder off of its surface, so we don't have to launch all that mass from the Earth's surface, collect enhance the gravity tractor's capabilities. And then there's the nuclear option. And if you saw Armageddon, now that's not how we would do it. If you blow up the asteroid, that doesn't disintegrate all that mass. All that mass is still on that same trajectory, and instead of having a bullet hitting the Earth, we got buckshot hitting the Earth. And it spreads out that area of devastation. A more artful way of using a nuclear device is to have a standoff explosion from the asteroid. That causes a shell of material on that side of the asteroid to be superheated and blows it off. And so that creates an instantaneous jet, if you will, of material going one way versus the other, and changes that velocity of the asteroid. It's also can be tuned, so to speak. If you don't need to move it so far, you don't detonate the device as close to the asteroid. You stand off a little further, or if you need more material blown off, you get closer to the asteroid. We're actually working on some of these techniques, and kinetic impactor, and in particular, since it's the most mature, the most likely object that we could be faced with is a smaller size asteroid, maybe in the 100-meter class. And so the Dependable Asteroid Redirect Test, DART, is in development at NASA now. We just had the preliminary design review a couple of weeks ago, and we're entering into decision point at NASA whether to take this mission forward or not here in the end of May. There's a system called Didymos, a binary system, asteroid that is about half a mile across, 700 meters. It has a small moon about 140, 150 meters in size, orbiting it. And so we'll demonstrate the kinetic impactor technique on the moon and change the orbit of the moon and determine how effectively we could do that. That has the benefit of, first of all, it's a fairly small object, so we don't need the impactor to be all that big. And second, we're only changing the orbit of the moon about the primary and not the orbit of the entire system around the sun. So we're not increasing the danger to the Earth by doing this experiment on this particular object. And we observe the effects on the system. The reason we've chosen this object is it comes close to the Earth in October of 2022 when we're going to do this encounter. And we're able to observe the asteroid after the encounter with ground-based observatories and radar. It'll be close enough to be in radar range so we can determine exactly how effective we were with this mission. Oops. Well, my movie's not going to run apparently. Well, bummer.
Bottom left.
Well, that changes the slide. Oh well, I had a nice movie of the impactor hitting the asteroid. These things never work when they're supposed to. So, Planetary Defense Coordination Office, we have 3 flight missions, either in operation, as in case of NEOWISE. Double asteroid redirect test is in development for launch, and actually, because we've modified the trajectory of the spacecraft, the launch won't be until 2021 now, but impact in 2022. And we're also trying to develop improved capability for detection and tracking of this object so we can get the entire population into our catalog of 140 meters in size. This is in phase A, and we hope to be able to corral the funding here in the next couple of years to be able to take this mission forward as well. Such a capability will be able to find that entire population of 140 meter and larger objects in about 10 years. At current rate, it's going to take us about 3 to 4 decades to do that. Lastly, I want to talk to you about a mission that is in flight now. It launched back in 2016, and in August you'll start to hear about it because it approaches its target. This is a sample return mission called the Cyrus Rex. It's going to the asteroid Bennu. Bennu was found back in 1999 by one of our near-Earth object observations projects, linear actually. Bennu is about a quarter mile in diameter. Has this spheroid shape, but what we call the muffin shape around it because this is body composed of loose material, and so as it rotates, this loose material migrates to the equator, and they get this ridge, this equatorial ridge. That's what causes that. Bennu is in a very Earth-like orbit, but goes out almost as far as Mars. And it is inclined to the Earth's orbit just a little bit, about 5 degrees. We've used all our assets to characterize this. Bennu is one of the most characterized near-Earth objects that there is. This is one reason why we chose it as a target. Again, Bennu size relative to some things, rotation period, orbital period, So Cyrus Rex, another tortured acronym. Origin, Spectral Interpretation, Resource Identification, Security, and Regolith Explorer. It has a sample arm that's going to touch the Earth's, the asteroid surface, kind of like a vacuum cleaner head. As it touches, it expends this gas, which blows material up into the sampling arm. And so that's a sample that then puts it into a capsule, return capsule on the spacecraft. The material collected off this asteroid will lead to a lot of work after its return. I think we can determine things like the origin of some of the material in the solar system. How did the solar system evolve? Might the asteroids be a source of life on Earth? And also provide us valuable information about near-Earth asteroids and what their characteristics are. As I said, it gets to Bennu this fall. Launched back in September 2016. I was at this launch. It was a particularly nice launch. It was almost at sunset, the sun being behind us. So the launch and the contrail is very nicely illuminated. It went through a gravity assist with the Earth after about a year after launch, and that's what's put it, modified it into the inclination of the asteroid using the Earth's gravity to do that. It begins its approach maneuvers this fall. Operations, close proximity operations of the asteroid. It will collect the sample and then depart the asteroid in 2021, and the samples get back in late 2023. After the gravity assist, it took that picture of the Earth and the Moon that I showed you earlier. Also took a very nice portrait of the Earth at its closest approach. The closest approach was over the Pacific. This is the Pacific Ocean here. You see Australia down here. That's China. This is the U.S. up here, the Baja California right there. So look forward to the news of Cyrus Rex this fall. And you can follow it in all of the social media. And with that, I ran a little over time, but I'll be here until you exhaust me on questions, because I can talk about it all night.